Hey, thanks for having me. So I'm from Franklin Marshall College. I just wanted to say, I don't actually have a lot of work to show you today, but to the extent that there's new results in here, they are partly in collaboration with a student at Franklin Marshall called Anton, and he's amazing. I picked him up as a sophomore, and he's been doing a second-year student. Second-year student. Yeah, sorry, a second-year student. Undergrad, and he's been doing pretty amazing stuff for that age. Okay, so toward object-oriented dynamics models in Atari. What is that? What are we even going to talk about? I basically have too many slides and not enough to say. So I think what I'm gonna make. Hopefully, I will make enough sort of unsupported proclamations to make this talk interesting. But what do I what's hello? Okay, putting that down. Nope, we're still okay. I want to talk about model-based reinforcement learning, and just as a quick cartoon of what I mean by that, like say we're playing a video game. This is Pong, where there are these two paddles and they move up and down, and there's a ball, and you try to get it past the other person's paddle. And so the agent, who is a smiley face, can interact with the environment by taking actions in some capacity, and can receive observations about the environment. And that's all great. You can learn about the environment just by interacting with it directly. But in model-based reinforcement learning, we kind of want our agent to develop a small version of the world in its head that it can imagine, and then it can, on its own time, when it feels like it, maybe interact with this small version of the world in its head. We call that the model, right? So it has this sort of model of the world that it can interact with. And as the title suggests, I got kind of interested in trying to represent this model using objects and relations and relationships and stuff like that. And I want to just confess right up off the bat that I have a long history of being really skeptical of this idea. A few years ago, I would have said, object? What's an object? Like, that doesn't make any sense to me. But I sort of got interested in it. And let me maybe make some unsupported proclamations about why. So I just want to talk about model-based reinforcement learning at a high level for a second. So we're going to interact with the world, and we're going to interact with the model. And one of my questions is sort of, well, what is all that interaction for? Like, what can you get out of it? And new data from the world is useful in a lot of different ways. So one of the ways that it's useful is that you can use it to refine your parameters of your value function or your policy or whatever it is that you're using to make decisions. And another way that new data is useful is you can use it to maybe propagate information about what states are good and what states are bad back through the dynamics. If you're just interested in these things and you want to use a model to do more of it, then probably you can do okay by just replaying things that you've already seen. Right? If your model is good enough to sort of remember what has already happened to you, and it can kind of reproduce what has already happened to you, then you can use it to do more updates on your function approximator or propagate value through your model. But there's other things that new data is useful for. For instance, if you try to do experience replay, one of the problems is it's stuff that happened a long time ago. And maybe you used to behave differently back then than you behave now. And so one thing a model could let you do is get some, I can't remember which button to press, there we go. Get some on-policy experience, right? So you could reach back into your past and think about a thing that happened to you and say, oh, well, what would have happened if I had done something different, something that I would do now? And so in order to do that, you need your model to do more than just remember what has happened to you. You need it to now be able to imagine taking a different action and imagine what might happen as a result. But there's even more that interacting with the environment gets you. For instance, exploration. So what is exploration? That is coming across new things that you've never seen before and that might qualitatively change the way you want to behave. Right? So you might find a new situation and just be like, oh, I've been doing it wrong the whole time. I should have been trying to achieve this. And if you want to use your model and you want data for interaction with your model to be as useful as interaction with the world, then your model needs to be able to provide this too. Which means your model needs to be able to imagine reaching a qualitatively novel state, which is about generalization, right? I mean, this is about, your model needs to be able to generalize in a sufficiently powerful way that it can replace real experience in terms of exploration, if you want it to be as valuable as interacting with the world. But what if you want it to be even more useful than interacting with the world? Like, could interacting with the model be even more useful? And I would say yes, if it can give you goal-directed updates. In particular, if your model is capable of imagining a desirable state, a goal somewhere out there, and then you can explicitly use your model to plan to reach that state, then that's even more useful than stumbling around in the world trying to run across that state, right? As I've been thinking about this is sort of why I started thinking about objects, is because if I want this, then it kind of feels like I need objects. So a lot of people have been doing models lately that are sort of image to image. They kind of take an image and then they sort of predict a next image. And it seems to me that there's a problem with that. A bunch of problems. For instance, let's think about generalization. Let's look at Pong, right? So here you are in Pong, you've got the paddles, you've got the ball, and if you are doing some convolutional neural net and you see, oh, the ball came from this direction, and now you want it to learn, oh, well, the ball should, and the ball should go there, right? Or maybe you see the ball came from this direction, and you want it to learn the ball should go there. Well, from an image perspective, from a pixel perspective, those are completely different situations, right? I mean, this is a totally different image than this image. But come on, that's not, I mean, they're the same, right? The ball just moves in the direction that it's moving in. So there's sort of like a discreteness and continuousness thing here. I would like more continuous representation, I guess, is what I mean by that. Also thinking about generating states, like if you want to do this thing where you like imagine a desirable state and then do something with it, you want to generate a state out of nothing that you've never seen before. Well, if you're in image space, you have to generate a plausible image, right? And there are thousands of pixels. And how are you going to set those pixels to make an image that looks like an image that you might see? Whereas if you have objects, well, then you just have to put objects together like Legos, and now you have a situation, right? So maybe that's more plausible, I don't know. Prediction errors, if you make an error in an image, you get incorrect pixels, right? So if you make an error in Pong, you might have white pixels where there would not be white pixels, and now all of a sudden you have two balls. What are you supposed to do with that? Like, that's not, a small change in the image can be a giant change in the state. Whereas if we had an object-based representation of this thing, I don't know, you get the positions a little bit wrong, then the positions are just a little bit wrong. Like, maybe that's not so bad. And then I was thinking about computational efficiency. It really bugs me that in all of these convolutional neural net models, that the complexity is dependent on the resolution of the image. Like, if I upscale my Pong, should my model get more complicated? Like, that's bonkers, right? Instead, it should be about the complexity of the scene, which is, again, kind of about objects. And then the thing is, though, that as far as dimensionality, like in terms of learning a function, there's this issue, and I think it's why we all want to do images, is that images are fixed dimensional. Here are the pixels, they're the input, here are the pixels, these are the output. And then for objects, not. There are different numbers of objects, and they may come and go, and that's challenging. Yeah.
Can I ask a question now?
Please.
Could there be some environments where no reasonable compression of the environment in terms of object-based model exists?
Yeah.
But those are not of interest?
Of course they are. So I'm really just kind of musing about objects because it seems like to the earlier point that it seems like in order to make the most of our models, they need to radically generalize, right? They need to be able to tell us about reaching situations we've never seen before. They need to be able to generate plausible states that are not like states we've seen before, but we might like to see. We need some kind of structure in order to make that possible. And so it seems like object structure would be useful. But I would always hope that whatever agent we come up with could hopefully exploit structure if it's there and maybe not be too harmed if it needs to give up on, like if it's not there, then it should maybe be able to back off onto something that's slower but less structured.
Maybe I can ask this question differently.
Yeah.
Could there be environments where any model that we have does not allow us to predict the future any faster than just observing the actual environment?
Seems like it.
Like, is that a problem? Because that would disallow us to do the experience, like actually use the model in the way for planning, which
right.
seems to be where you're driving with this, right?
So I guess I don't see it as a problem. I am interested in model-based reinforcement learning not because I think it is literally the only way to go, but because I think it is probably useful in a lot of cases. And if I could imagine my dream agent would be able to do model-based reasoning when it's useful and not when it's not. So there's this issue. It's a challenge, right? It sort of ruins everything we think we know about function approximation. Now there might be a different number of inputs every step and different number of outputs, and what do we do about that? But luckily people have been thinking about this, people much smarter than me, people who actually are the world's experts on model-based reinforcement learning. And I know I promised in my abstract that I would tell you about some of that stuff, but I think I don't have time to I have diagrams and stuff that I would love to show you about some of the architectures people have been working with. But I think that was a bit ambitious. So instead what I want to just lay out are some general principles about how people are thinking about how do you deal with this sort of variable number of objects issue. And then if you want later I could show you some actual concrete networks that apply these principles. So one thing people are doing is that because we don't know how many objects there are, we can't just like concatenate all the objects together and call that our input, right? So instead, we're effectively going to convolve over objects. So in convolutional neural nets, we convolve over the image. We apply the same network to every position, right? And we get an output for every position. So it's the same idea. We're going to take one network and we're going to apply some transformation to each object, right? So each object is going to be represented by some properties, and then we're going to take some network and apply it to each object and get an output for each object. So there's something that's going to reason about objects individually, right? And then we need somehow to get information about objects to other objects, right? And so there are various ways to do that, but overall, I think generally the big idea is that we're going to combine all those individual object outputs into some fixed width context. Somehow, we're going to get all the information. We're going to get the information we want out of that stuff. We're going to combine it somehow, and usually it's with some form of pooling that is permutation invariant. So it doesn't matter what order the objects come in. It'll be like a sum or a max or a mean or something like that. Yes?
How can you tell what an object is?
Yeah, I know, right? I'm going to sort of not very satisfyingly answer that question in a minute. And then you have this sort of shared context that has hopefully pooled together relevant information about all of the objects. And then you combine that shared context again with each individual object state to make a prediction for each individual object. So you have this, it's sort of like a convolution to gather information about all the objects, and then another convolution to use that gathered information to make a prediction about each individual object. And there are a few different sort of architectures out there that kind of do this in various ways, but I think these are sort of the big ideas that are going around. Did that make sense? I know it was abstract. I just want to tell you a little bit about where I'm headed with this, even though it's not very satisfying. But there's a problem with most of what people have been doing, Namely, the big one is that, as you pointed out, Martha, that people assume that that object identities are just given and they're perfectly reliable. And so you sort of know what your objects are, and you know what their states are, and you can track them across time, and all of this stuff. And that's not going to work, right? Like, where are the objects going to come from? Like, you give me an image. What are objects, and how do I identify them? And furthermore, how do I track them over time? Like, if I see a red thing in this time step and a red thing in this time step, are they the same red thing? Are they two different red things? Who knows? And then also, how do you deal with errors? Like, even if you figure this stuff out, it's not going to be perfect. And sometimes you're going to misidentify objects, you're going to mismatch things, and you're going to have to deal with errors. And none of as far as I know, the existing work just doesn't cope with that. They also tend to assume the number of objects is constant, not constant. Like, the network is agnostic to the number of objects, but they assume the number of objects doesn't change, right? And that's a problem too, because objects come and go, right? Like, things are here and then they're not. And then also generally they output expected object state, which can be an issue. Like, sometimes there's actual uncertainty, and then the expected value might be weird, right? So, like, if you don't know whether the ball is going to be here or here, the expected value is that the ball is going to be here, which is neither of those places, and is probably not a sensible thing to think about the ball. So I kind of have been playing with, well, what could we do about this stuff, in particular in the domain of Atari? Like, I basically have sort of got interested in, well, it would be nice to have objects. And then I was like, well, what are people doing about objects? And this is kind of what they're doing. And then I thought, well, that's not enough. And so I wanted to just see what would happen if we tried. So we did some really quick and dirty stuff to try to get past these problems without working too hard on them. So because we're in Atari, we can kind of specialize a little bit to this particular domain, just so that we can hopefully get to the point where we can actually study the modeling part, right? And not get completely bogged down in all these other questions. So what are objects? Well, in my model, objects are just blobs of nearly contiguous color. Yes, Adam? 5 minutes, thank you. So they, by nearly, I just mean there's a little bit of give in the contiguity, so they don't have to be next to each other. But so you take this Pong screen, and then where are the objects? The objects are there. There are a lot more of them than you probably would have listed, right? Because, well, that's a blob of contiguous color, and this is a blob of contiguous color, and there's this weird black line in the corner of the screen for some reason, and that is also a blob of contiguous color. This 8 is not 3 blobs because of the nearly contiguous thing. So these brown bits got blobbed into this big blob. So there are more objects than you might have thought. But hey, we've got objects. We still have to track them over time. And so what we do is we just do greedy proximity matching. So we just say, hey, are you a red thing? Oh, there was a red thing in the past time step. It's closest red thing to you. You must be the same thing. You'd be surprised, actually, at how well this works. I was surprised. I had Anton. I was like, Anton, get me objects. And he was like, this is what I'm going to do. And I was like, that's not going to work. And it did. It basically did. So now we have to deal with blinking objects. We're in Atari. Objects can blink. They can come and go. There can be errors in the blobbing. So how are we getting object permanence? Well, when an object disappears, we just sort of keep it in memory for a while. And then when an object appears, we try to match it to one of the invisible objects that we have. And if we can match it, then we just treat it as the same. Object state is just color, position, velocity, and visibility history. And we predict position and visibility. And the way we get away with that is by when the object turns invisible, obviously we do not know what position it ought to be in, so we just don't give any position error in those cases. So this is our really quick and dirty, horrible stuff that we would obviously like to rip out and replace with something more general, but we're just trying to get to a place where we can actually study this. And And importantly, it doesn't predict the appearance of new objects. So this is actually a big limitation that we still have to address. But in Pong, it's not a big deal. In Pong, you mostly are worried about objects disappearing, not so much appearing. And then to deal with this uncertainty question, I've been using an implicit quantile network on the end of this network, which is a kind of a new thing. I don't have time to explain it to you, but you should read it because it's cool. And it's a sort of a generative implicit distributional model.
Appearance of new objects.
Yeah.
We score in Pong. When 8 becomes 9, is it a new object or is it still?
It thinks it's the same blob. Like there's still a blob of that color. The fact that it has changed shape is irrelevant in this particular thing. Yeah.
When 9 becomes 10?
Yeah, that's a new blob, but it doesn't really matter because you predict the score using what happens to the ball, right? Like you don't wait for it to turn to 10 and then say, oh, +1. It turns to 10 at the same time as the +1 is happening because the ball has just gone off the edge of the screen, if that makes sense. So you're right. Like it's not that objects don't appear in this game. It's just that I think that not predicting them is not a big problem. Oh, look at that. I'm out of time. So anyway, there's this paper. I recommend reading it. And then there was a whole bunch of other stuff that we had to worry about. I feel like people kind of hide a lot of the work that they do on neural nets. So just as an effort to not do that, this is how I have spent my summer. And I don't have a lot to say about this stuff because honestly there are just way too many knobs to turn and it's very hard to study it all, and I don't have any good science on what matters. I think that some of it has mattered. It's better than it used to be because of some of this stuff. One day, if it gets to a point where it's doing something useful, I hope to go back and understand why it works, but I can't tell you now. All right. I'm out of time and we have to decide what to do. I think what I want to do is show you real quick I want to show it to you. I want to show you it working. So, and I'm going to do this very, very unwise thing that you should never do, which is show it to you live. So this is just Pong, no predictions. Go ahead, do your thing. There we go. So there's Pong. I'm not showing you any predictions or anything. This is just what it looks like in the blobbed image, right? So you'll notice, you see it turn gray up there? That's because the ball is the same color as the sidelines. And so when it gets too close to the sidelines, they get blobbed together and the ball appears to vanish. Also, the sideline appears to move for a second. It goes like that. So that's a challenge. Okay, so now let me show you some predictions. What I'm going to show you are the red dots are samples from, so this is the network is giving a probability distribution, and so the red dots are samples from that distribution. So you'll notice that actually you can't see the red dots in a lot of cases because it's doing a pretty good job, actually. And I want to point something out, like this paddle is the same color as that score up there, but it knows that they're different, right? It knows that the paddle responds to, or like this paddle responds to the action, but that score does not. That's pretty cool. It seems the object model that's trying to collect a shared context seems to be working because the opponent paddle is tracking the ball, which is what it does in real life. But in order to do that, it has to have information about the ball's position. And it's working. It's doing that. And you might also, if you watch carefully and you get a glimpse of it, you might see that it does an okay job of predicting visibility. So sometimes when the ball bounces off of the sideline, the particles turn gray too, but I can't, it's too late. We can also look at rollouts of this thing. So I'm going to turn the red predictions off and instead show you, so this is just one-step predictions from the current step. But now I'm going to let it roll out. So I'm going to let it take a sample, and then from that, take another sample, and then keep going forward. And you will see that it does okay. Like the ball went invisible when it should have. So here we go. So that was an interesting case because the outcome of the rollout was different than the outcome in real life. It was reasonable in the rollout because the paddle wasn't next to the ball. But that means it got the paddle wrong, right? It put the paddle in the wrong spot. And so you'll notice that that's what's happening in the predictions. There's a lot of uncertainty about the paddle. And that's because the paddle movement is actually surprisingly complicated. I think we were saying it's 17th order Markov.
Atari.
Yeah, and it can go really fast, and so it has a really hard time predicting where the paddle is going to be. So that's been a challenge. Anyway, as you can see, it seems to do some pretty reasonable stuff. Like I'm excited about that. Now let me show you how useful it is for planning. So here I'm doing Dyna with this thing. I'm just learning the model as we go, using it for Dyna as we go. And look, it's learning something. This is not a complete disaster. I work in model-based reinforcement learning. That's a win. Right? It's better than random. I'm happy. But if you compare this to Q-learning with no model updates, then you will see that it's not like we're not throwing a party about this. It's still not good enough. So where are we? It basically works. Like it knows a lot of stuff. It knows how the ball moves. It knows about bouncing. It knows about visibility. It knows about a lot of interesting stuff. It has distinguished different types of objects, even though they're the same color. That's very cool. But it's not good enough for planning. And it's very frustrating. Neural nets turn out to still be neural nets. It's still super fiddly. All that design space that I just put up there, I had to mess around with all that to get it to where it is, and it's still not good enough. It's still compute hungry. I thought this would be super efficient because it's only in the number of objects, but the bigger the network gets, the more complicated it gets, and that's frustrating too. And it's still super data hungry, which is very frustrating because I'm after generalization. I want to do a couple of games of Atari and be like, all right, I know how objects move, and that's not how it's working at all. What I just showed you, the visualization I showed you was after 10 million frames, right, which is way too many. And there's plenty more to do, obviously. This is very preliminary, very unfinished stuff. But one thing that I've noticed is it seems like this idea of convolving across objects seems to be pretty limiting. Basically, the first thing the network has to do is figure out what kind of object it's even working with, right? And that's an awful lot of effort. And it's especially an awful lot of effort for a neural net which wants to be smooth and continuous. And I'm asking it to be super discontinuous, right? And be like, oh, this object does this, and this object does this. And that's not what it wants to do. So maybe somehow we need more decomposed parameters in this model so that we can separately learn different things for different objects. I don't know how to do that. Obviously, we need to model appearing objects. You can't play Space Invaders if you can't predict that bullets are going to appear. So that's a problem. And it's a surprisingly challenging problem because there could be a variable number of objects appearing at any given moment, and those objects could be correlated with one another. Like if multiple blobs make up one object, then you might have multiple blobs that all appear together all the time, and that would be hard to model. And then the other thing, and this is something that's always on my mind and sort of my obsession lately, is just that I have to acknowledge that no matter how good we make this thing, it's not going to be perfect, right? And so there's still this question in my mind about, well, it's so frustrating, right? It knows so much about the world, but we can't use it for planning. Like, how can we take advantage of the stuff it does know, even though it doesn't know everything? Or alternatively, maybe we could somehow discover a level of abstraction where it can tell us stuff reliably, even though it can't tell us in full detail. So that was a whole lot of speculation and not a lot of science, but hopefully something interesting to talk about for the next few minutes. Thanks. Yeah.
So when you were were talking about all the pre-processing you have to do to extract objects,
Yeah.
I was thinking a group of people who've done a lot of work on this are the people who do video compression.
Yeah.
Because if you take a modern video compression codec, what they are doing is identifying objects. They are like figuring out how things move, so that you produce a very low complexity bit stream, and you have a small number of objects not moving very much, and you have high complexity bit streams, and you have lots of objects. And if you've seen a corrupted video, right, if a few bits are corrupted, they actually continue to generate plausible looking video for several frames
Yeah.
after that, right? So I was wondering if you took a modern video compression codec, and just pulled apart its bit stream, and that would be a good sort of space to do all the object stuff on.
It would be interesting. Like, definitely this is a really crude way to do it. So to be honest, the way it started, like I said, so Anton has always presented himself to me as really interested in vision. And I came home from a AAAI conference having seen a whole bunch of stuff about like optical flow and everything. And I was like, I want objects. You vision guy, give me objects. And I said, I'm probably going to hate what you do, but do it, and then we'll talk about it. And thankfully, to his credit, he started real simple, and it basically seems to be good enough for now. But absolutely, this is not going to last, right? Like, you want something that's more sophisticated than this. Blobs aren't going to work forever.
And I have another question, which is less sort of maybe more philosophical. So I was thinking about what Martha said, like, what is an object?
Yeah.
And in physics, sort of the reason that we have objects is we have a bunch of things that all have similar properties. So instead of keeping the properties of every single particle, we say all these particles are doing the same thing, so let's just lump them together into an object.
Yeah.
And the properties that you care about in physics are the things that you need to predict where the object's going to go next.
Yeah.
Right? So in particular, in Newtonian physics, it's position and velocity. Right? So in some sense, the definition of an object there is a bunch of things that are all acting in the same way.
Yeah.
And sort of the dynamic sense of it, right? And there's this sort of view that this is sort of the simplest way of doing physics, is that you have this giant representation, which is like, let's say, every pixel. But then, and you define sort of an energy function on that. And then it turns out that there is this sort of much smaller representation, which has all the information that you need. So I guess this is hand-wavy, but what I'm saying is that all of physics is a representation learning problem, going from large state spaces to small state spaces. And there's a lot of parallels between what we do in RL model building and what physicists do, because they are doing model building just for a different environment.
Yeah, that's cool. So I did spend a little bit of time. I should also say, I know I'm over time. If you have somewhere to be, I will not be offended if you get up and leave. That's I just want to make sure you know that. I did spend a little bit of time at first worrying about extracting objects from the images. And I was trying to do this like weird autoencoder thing and trying to treat objects as like a sparse encoding of the image, where you could easily like just take this very sparse encoding and then reproduce the whole image, because all you need to know is like, this is a chicken, and then it just draws a chicken, right? But it didn't work, probably because I'm not smart enough. But like, absolutely, I think there's something there about objects as purely a sparse, low-dimensional encoding of the bigger space, and I just don't know how to discover it, but that's worth exploring. Yeah.
But it seems to me, following up on that the appropriate level of sparsity depends very much on what you want to do.
Yeah.
So if you accept any outcome in ping, in Pong, in any game, right, in Pong, then empty model isn't good enough, right?
Yeah.
You're just going to do nothing, and you behave exactly how you want to do nothing, right? If you want to, write poems about it, that's a different level of model. If you want to move the paddle, it's yet a different level of model. So I keep hearing the word, what do we need in a model?
Yeah.
And that seems to be tightly correlated with what
you want to do.
Is, right?
Yeah. Yeah, I go back and forth on that kind of stuff, because on the one hand, I feel like one of the dreams of model-based reinforcement learning is that you can learn your model before you know what to do, right? But if your model has to be task-specific, then you kind of have to wait to find out what you need to do before you can learn your model. And so I always kind of hope that there are ways to think about useful predictions to make in the world.
Useful for what?
Exactly. I know. And then it doesn't mean anything, right? And then like I do honestly go round and round on this, and I don't have a way off the merry-go-round. It just, yeah. But But what I will say is it does seem like there are problems where if you apply the right kind of structure, the right kind of generalization bias, then you can learn a model way faster than you can learn a policy. And so then the question is, can we exploit that structure? Like, that's really what I'm worried about. And then like unraveling that issue is a whole other question that probably the answer is like our agents should be able to do lots of things in lots of different ways, and that but we have to study things kind of in isolation or else we'll go crazy. Oh, yeah.
So, in the results that you showed, there are a lot of moving pieces, right?
Yeah.
You have the network, you have the object detection, you have the planning algorithm that has to do something with that. What if you had the objects? I know that a lot of the assumptions here is like, it's imperfect and,
yeah.
But you can actually extract the objects in Pong.
Sure.
And if you have a perfect object model, you still don't have a perfect model to the result. Does it change anything, or it's like you already have a good enough object detector that now the problem is on everything else?
I think in Pong, the blobs are pretty good. I think the only real blobbing problem is, okay, there are a few things that come up. So one is the ball in the sideline, which it seems to be able to handle, which I was super pleased about. The other thing is that because we're doing this by color, it has to learn to distinguish different objects that are the same color, right? And if it had perfect objects, it wouldn't have to do that. So that would probably help. But I don't know. I suspect that that's not the issue. So I think currently my hypothesis about why this is not going as well as I think it should is this issue about neural nets and applying one global net to every kind of object dynamics. Like I think that there's enough uncertainty in the world where the paddle is just super uncertain, and there are all kinds of special cases, and it's just having a hard time carving up the space to find all the different special cases. That's sort of where I am with it right now. And then the other thing is that I think it just will never be right. It's going to be wrong about the paddle for sure. And then the question is, what do we do about the fact that it's wrong about the paddle? That's a whole other kettle of fish, though.
But that's a different question, right?
Yeah, it is.
It will always be right about the object paddle. Let's say this. I mean.
No, that's what I'm saying. Like the dynamics model, unless you give it.
Yes, that's what I say. It's like there is a difference between the object itself and the dynamics of that object.
Yeah.
Right. It can be always right about the object.
Yeah.
I want to say that humans are not going to make wrong assumptions about the paddle's existence, but they will not be able to predict exactly the position that the paddle is going to.
Yeah. So it does absolutely, this issue where it has to distinguish these different objects of the same color does show up. Like if you look at rollouts in the low data regime, and by low data I mean thousands of games, right? It's still, in fact, I've even seen it, this model that I showed you, I've seen it happen. It just didn't happen to happen when I was showing you. But like, you will every once in a while see a score blob dislodge from the top of the screen and come down and start acting like a paddle, right? Like every once in a while, it just takes one little nudge for it to be off position, and then the network is like, oh, look at this blob, it's not in the score position, must be a paddle, and it just goes with it. So yeah, definitely, and a human would never do that, right? A human would never make that mistake. So definitely there's an issue there with the object detection. I'm just not in a rush to fix it because I'd rather deal with the ambiguity. Yeah.
Could you bring up your list of what models can help with for a second?
Oh.
It was right toward the beginning.
Oh, what models? Oh, yeah, that one. I like that slide.
I like that slide too.
I
kind of wanted to ask, sort of your conclusion is, we did all this modeling work and our model's still not good enough.
Yeah.
But how much do you think? Part of it is your planning algorithm, right? So,
yeah.
So what do you think Dyna, as you've implemented it, what you've done with Dyna, what do you think it's able to grab of these ideas?
Yeah, that's a good question. And actually, I forgot to do a thing that I totally meant to do, which is to say that in this distinction here, there's more to say about this, and you should come to Zach Holland's thesis talk tomorrow, because I think it's highly relevant to this. And I don't want to steal his thunder, but just to say this, that the DINA algorithm that I'm applying is pretty much just one step of planning. Like you pick a state that you saw, and then you roll the model forward one step, and that's a lot like experience replay. It's not clear that that can show you something genuinely new. And so I think Zach has some results that sort of show that if you really want to get the most out of, you want your model's data to be equivalently useful to the world's data, you need to do something other than that. You need to somehow use your model to generate genuinely new stuff to get the exploration benefit, as well as this other stuff. But can DINA do this? It can, right? If you have a state generation process, if you have a way to propose a state that you've never seen before, and then start doing updates around there and from there, maybe DINA with a reverse dynamics model or something.
So what I kind of wanted to ask is, where do you think, like maybe you say, my model's not good enough.
Yeah.
But maybe it's because you're not trying to pull in these other...
Yeah, maybe DINA's not good enough. So the reason I'd say that the model's not good enough is that it is still, like it is qualitatively, you can tell that it is wrong about important stuff, right? So it will do a poor job of predicting whether the ball is going to bounce off the paddle. And I understand why, like there's a lot of uncertainty about that, and there's lots of special cases, but if you get that wrong, you're probably not going to be very good at Pong. So I do think I have pretty good, just from experience of staring at this visualizer too much, I think I can say that the model is genuinely bad at some important stuff. But that's also, I don't want to take all the responsibility away from the planner. Like, it would be nice if the planner could cope with that, right? If the planner could say, well, you're just bad at this, I'm not going to listen to you. Now we're really over time. Thank you for your attention.